In the previous video, discussed matrices which are in echelon form, and we are going to continue with that. So we are going to continue also with Gauss elimination, and we'll start off with definition 2.3.5 in the textbook, and it says the process of Gauss elimination consists of the application of elementary row operations to the augmented matrix AB, corresponding to a system of linear equations to obtain an augmented matrix CD with matrix C in row echelon form. So basically, that's what we need to use to be able to to get an augmented matrix where the matrix is in echelon form. We'll use Gauss elimination. And then, so we have got a theorem, and it says consider two augmented matrices A, B, and C, D, with A and C both M by N matrices, and a vector X in Rn. Now, if AB is row equivalent to CD, then AX equals to B, then AX is equal to B if and only if CX is equal to D. So in other words, what it means is if we use Gauss elimination to reduce an augmented matrix to echelon form, then the solution that we get for the um, for the new system Cx is equal to D, where C is in echelon form, is the same as the solution that we would have gotten. Well, it will be the same solution that we get for Ax is equal to B for the first system AB. So what it means is we can use Gauss elimination because we know that AB will be row equivalent to CD if we use the elementary row operations. So therefore, we will get the same solution. So basically solving the system when the matrix C is in echelon form will make our life easier. And then theorem 2.3.7 says let A be any M by N matrix, then there exists an M by N matrix B in row echelon form so that A and B are row equivalent. So what this one is saying is that if you are given any matrix A, then you can reduce it to row echelon form. That's what it's basically saying, right? So in summary, theorem 2.3.6 states that if Gauss elimination is applied to the augmented matrix AB corresponding to a system of linear equations, then the system of linear equations corresponding to the resulting augmented matrix CD has exactly the same solutions as the original system. And theorem 2.3.7 states that the process of Gauss elimination can be applied to any system. Right, so that gives us ammunition to be able to solve any system of linear equations. So let's look at an example where we are going to use Gauss elimination to solve the system. So this is example 2.3.8 in the textbook, and it says we solve the system of linear equations where the system of linear equations is given as that. Now, so we are going to apply Gauss elimination to the augmented matrix corresponding to the system of linear equations. So if we write it in augmented matrix form, this is what it will look like. And so the first thing is we want the value here where there's a 0 to be a non-zero, and the way we achieve that is to interchange row 1 with something, either row 2 or row 3. In this case, we use row 2. So we do the elementary row operation R1 interchanged with R2, and we get now the row 2 is now the new row 1, and then the row 1, the old row 1 is now the new row 2, right? So we have that. Now the next step, now here we've got a 0. So here we've got a non-zero. There we want it to be a 0, and it's a 0, so that helps us. We also want this to be a 0, this value on the third row, the first entry on the third row, to be a 0. So how do we achieve that? Well, if we look at it, we'll see that if we say 4 minus 2 times 2, we'll get 0. So in other words, we can say R3 minus 2 times R1, and then we'll achieve what we want. So if we say 4 minus 2 times 2, which is 4 minus 4, is equal to 0. 5 minus 2 times 3, which is 5, minus 6, which is equal to minus 1. Minus 2 minus 2 times minus 1. So minus 2 plus 2, we get 0, right? And then if we say 10 minus 2 times 7, which is 10 minus 14, is equal to minus 4. So we have that. Now the next step is we can see the element on the diagonal there is a non-zero. So what we want is this value to be a 0. What is below 1 should be a 0. How do we achieve that? Well, if we say minus 1 plus 1, we get 0. So in other words, we want R3 plus R1, right? So if we say R3 plus R1, we are going to say minus 1 plus 1, we get 0. 0 minus 3, or 0 plus minus 3, we get minus 3. And then minus 4 plus minus 5, which is equal to minus 9. And now the system is in echelon form, right? Or the matrix is in echelon form. So now when we get to echelon form, we can easily solve the system of equations. So so we can rewrite the system now. The new the final system will look like this. And so therefore, by looking at the third equation, we can see that x3 is equal to 3, just dividing by minus 3 throughout. And then if we put that x is equal to 3 in the second equation, we find that x2 is equal to 4. And then if we plug in x2 and x3 in the first equation, then we'll see that x1 is equal to 1. So therefore, the solution is x1, x2, x3 is equal to 1, 4, 3, and it is a unique solution. Now let's look at another example. This is example 2.3.10 in the textbook, and it says we solve the system of linear equations, and we've got a system with 4 unknown variables, or 4 unknowns, right? So we again apply Gauss elimination to the augmented matrix. So so the first thing, again, we've got a non-zero there. We make everything that is below it a 0. So we want to make this a 0 and that a 0. So if we use the if we want to make this a 0, we can say 4 minus 2 times 2, right? So in other words, R2 minus 2 times R1, which is this row operation. And so if we say 4 minus 2 times 2, that's 4 minus 4, which is a 0. And then 10 minus 2 times 9, which is 10 minus 18, which is minus 8 there. And then we've got minus 20 minus 2 times minus 2, which is minus 20, plus 4, which is minus 16. and then we have 3 minus 2, which is 1, and then 0 minus 0, which is 0 there, right? And then now we also want to make this a 0, so the next row operation is that one, because we just say 2 minus 2. So in other words, R3 minus R1. So if we say 2 minus 2, we get 0. If we say 5 minus sorry, if we say 8, sorry, if we say so we say 2 minus 2 is 0, and then we've got 5 minus 9, which is minus 4. If we say minus 2 minus minus 2, so minus 2 plus 2, we get minus 8. And if we say 11 minus 1, we get 10. And then if we say 0 minus 0, we get 0. Sorry, I had to catch my breath there. So now we've got zeros there. So if we look at the next the diagonal entry there, it's a non-zero. So we want to make whatever is below it as 0. So what kind of row operations do we need? So if here we would want to say minus 4 plus 4. So for us to get a plus 4 there, we have to say minus half of minus 8, right, to get plus 4. So in other words, we can say R3 minus half R2, right? So 4 minus half times minus 8, which is minus 4 plus 4, which is 0, and so on. So we can do the elementary row operation. We can for us to have 0 here, we say 8 plus minus 8. So therefore we have R4 plus R2, and then we get our 0. So we'll end up with something like this. So for the first operation, we have that. For the second operation, row operation, we've got that. So and now the system is in row echelon form. Why? Because the zeros are at the bottom. The row of the row with 0 entries only is at the bottom, and we can see that minus 8 is to the right of 2, and 9.5 is to the right of minus 8, and so therefore we have what we need for row echelon form. So if we write this system again, we have 0 is equal to 0 for the last equation, and from the third equation we can see that x4 will become 0 from that one. Now if we go on to the next one, so we would have wanted to find x3 in this one. We find out that if we put our x4 is equal to 0 in the third equation, or sorry, second equation, we end up with minus 8x2 minus 16x3 is equal to 0. So what this means is we can't really determine x well, x3 and x2 cannot be uniquely determined, because we should have just plugged in x4 and then get either x3 or x2, whichever was going to be there. But here we can see we still have two unknowns in this equation. So this means that x2 and x3 cannot be uniquely determined, right? So what do? We take x3 to be some constant, some r, where r is a real number, and then we find x2. So if we do that, here we put our x3 is equal to r, we find out that x2 is equal to minus 2r. And if we do that back substitution into the first equation, so x4 is equal to 0, x3 is equal to r, x2 is equal to minus 2r here, then we find x1. We will find out that x1 is equal to 10r. This is supposed to be x1. Then, so therefore the system has infinitely many solutions, and the infinitely many solutions look like this. So x1, x2, x3, x4 is equal to 10r, minus 2r, r and 0, where r is a real number, right? Okay, so the first example that we had a unique solution. The second one, we now have an infinite number of solutions. So we're going to look at the third uh, example, which is no solution. So we are given a system of equations, and this one is has two unknowns, x1, x2, right? So if we apply Gauss elimination to the augmented matrix, what we have is, so the first augmented matrix will look like this, just taking all those values and putting them there. And then in this one, they started off with making this a 1, the first entry to be 1. So how do you do that? We can divide half by half the whole row. So in other words, R1 goes to half R1. So we get 1, 1, 1. Now we want to make whatever is below this 1, the entry in the diagonal, to be 0, zeros. So we want this to be a 0, we want that one to be a 0. How do we do that? If we do that, then we have so for us to do that, we can say 2 minus 2 times 1, right? So in other words, R2 minus 2 times R1, right? And then so if we say 2 minus 2, we get 0. 3 minus 2, we get 1. Minus 1 minus 2, we get minus 3. And then for the third row, for it to be a 0, we just say 1 minus 1. So in other words, R3 minus R1. So if we do that, 1 minus 1, we get 0. Minus 1 minus 1, we get minus 2. And then 1 minus 1, we get 0, right? Now, so the next step would be for us to be able to, so that is an entry there. The next entry will be, this one is a non-zero, so we want anything below it to be 0. So we want minus 2 to become a 0. How do we do that? Well, we can say minus 2 plus 2 times 1, and then we get our 0. So in other words, we can say R3 plus 2R2, and then we can get our 0. So minus 2 plus 2, we get 0, and then 0 minus 2 times minus 3, sorry, 0 plus 2 times minus 3, so 0 plus 6 ish, sorry, it's 0 minus 2 times minus 3, which is 0 minus 6, which is equal to minus 6. So in the end, here we are supposed to have 0, 0, and minus 6. So this will be corrected in the PDF to on the that will be put under Dr. Madana's notes, but this is 0 there and minus 6. So in the end, we are left with x1 plus x2 plus 2x2 is equal to 2, x2 is equal to minus 3. Okay, this one is a problem again. So it's x1 plus x2 is equal to 1. X2 is equal to minus 3, and then 0 is equal to minus 6. So again, this will be corrected. Right. So if we look at the last equation, we can see that it amounts to 0 is equal to minus 6, which we know is impossible. So therefore, that means the system has no solutions. So we have had 3 examples, and we have seen 3 possible solutions. And in the next video, we are going to talk about, we are going to formalize that with a theorem that states that any system of linear equations is either a unique solution, no solution, or an infinite number of solutions. Right. Thank you.